Let's see if we can learn a little bit more about these quantum tunneling, imaging atoms or positioning atoms, and imaging electron orbitals. Tunneling, imaging atoms, field ion microscope, positioning atoms, imaging orbitals, and quantum computing. I think that's the final one. Ooh, quite. Each of these topics actually requires a separate book. Page 82. Quantum tunneling, formulation of QM, atomic matter, properties of atomic matter. Properties of atomic matter. Describe the properties of atomic matter. Quantum mechanics help us describe the properties of atomic matter. Practical consequences. What can we do with it? Situations in which the principles of quantum mechanics make a huge impact on our technology and beyond. Using our knowledge of atoms and matter, and using our knowledge of the quantum nature of matter, what can we do with it? Quantum tunneling. Wave function passes through a barrier spanning a region of space. Thicknesses, wave function. Not clear why this one is getting through and that one is not getting out, so the barrier is smaller. Wave functions, they do not come to an abrupt end in space. Depending on the system which they are in, they can diminish to zero over the span of the entire universe. So the wave function, that's a probability of something, the probability of finding the quantum unit there. So what they're saying is that it doesn't go to zero. It's not zero, but this interaction with another medium or within another space with other matter changes the wave function probably. A finite probability for a quantum particle to be found in places where classical physics says it shouldn't be. Figure shows a wave function for a quantum particle within a region of space that is bounded on the right by a barrier in energy that's higher than the energy level of the quantum particle. The barrier also definite width in space. The wave function has a sinusoidal side inside and outside the barrier, but within the barrier the wave function decreases. But within the barrier the wave function decreases exponentially. Zook. Okay. Quantum tunneling. The wave function of a quanta. Let's call it a quanta. it extends. Probability not zero. Barrier mathematical solution. The wave functions inside and outside the barrier. Within the barrier, the wave function decreases exponentially. Sinusoidal, but inside it decreases. Inside exponential decrease, outside sinusoidal. Okay. So they're looking at the wave function. What does the wave function tells us? What does it tell us about the quanta in this situation? That's energy. 82, 83. Everything still in view, yes. 3 solutions joined to each other. Non-zero on the right, unless the energy barrier is large. So it's the wave function. How does it behave in these 3 regions? In ordinary Newtonian physics, the particles wave function be a constant value to the left of the barrier, but inside the edge of the barrier, the wave function would immediately fall to exactly 0 because the particle has insufficient energy to surmount the barrier. The ability for the particle to be found outside its classical region is called tunneling. The time it takes for the particle to escape from the permitted region is very long when the difference between the particle's energy and the barrier energy is large, and it's very short when the difference is small. I talk something about time. The time it takes the particle to escape from the permitted region is very long when the difference between the particle's energy and the barrier energy is large. Quantum energy, barrier energy, time to escape. Wave function inside, wave function outside, quantum tunnel, exponential decrease, tunneling out of an atomic nucleus. Wave functions do not come to a abrupt end. They can be found with non-zero amplitudes outside classically bound systems such as nuclear. So we can expect such a thing from matter because the matter is concentrated in a very small region of space, but now this quantum unit, we're located in a very small, but according to the quantum concept, it's actually it extends much farther out than we think it is. It's extending. It's like it's slowly fading away. It doesn't have a definite boundary. It's the wave function. Continuous in the three regions. Time to escape. Particle found inside an atomic nucleus has insufficient energy to escape. Atomic nucleus, strong nuclear force, wave functions, these particles throughout space, even outside. Inside there is a large amplitude because the probability to find out inside it is higher. However, the wave function can penetrate the potential area, separating the nucleus from the rest of the atom. What? No, I don't think that's correct. However, the wave function can penetrate the potential area, separating the short range of strong. Okay. Nucleus. I think this is a textual error. Nucleus. What am I gonna say here? Energy well. Wave function. So keep on concentrating on the wave function. 82, 83. What does the wave function tell us about this situation? 83, 84. Is it still in view? 84. Nucleus, nuclear force, sinusoidal waveform, exponential decay outside the domain of the strong force, reduced amplitude. Time it takes to tunnel out of the nucleus is longer than the age of the universe. And it is stable. For other atoms, the tunneling time can be measured in seconds, minutes, and even billions. Call these atoms radioactive. It's a nucleus. Time to tunnel out. Stable, short, radioactive. Inside an atomic nucleus, alpha particle, central nucleus. Heavy nuclei can be considered as a collection of alpha particles. Are they alpha particles? That's the helium nuclei. 2 protons. I'm not sure. Is it 2 neutrons too? Alpha particles close to the top of the nuclear interior leak out, forbidden and classical. The body top of the energy well. Difference is large, stable, non-radioactive. Tunneling will take a short time. Use can be seen. That's why the half-life of some radioactive elements vary enormously, even though they may all primarily emit alpha particles during the decay process. I'm not sure what's going on here. Heavy atomic nuclear above an atomic mass about it consists a collection of alpha particles. Atomic mass. Atomic various energy, which are found at various energy levels inside the nucleus, similar to electrons of an atom. Oh, so energy levels. So even inside the atomic nucleus we found energy levels. So the energy of those alpha particles in the nucleus is also quantized. That one there, that one there. Top can escape. 34, 85. Let's move on before I realize I don't understand it. As soon as you understand something, move on. Half-life. Half-life. I think I write the G half. Half-life. Half-life is 1 minute. Half-life of nuclei. From short to very long. Practical engineering as an invention of transistor, electric device called tunnel diode. Sony Corporation, 10 nanometer wide junction that should behave as a resistor when the voltage is applied one way. A weak current of electrons flow by a tunneling process when the voltage is applied in the opposite direction. Also, it's the reverse current that is tunneling, it seems. So they're talking about the forerunner of the transistor, I think. Tunnel diode. I think it's the reverse current. Weak current of electrons flow by tunneling when the voltage is applied in the opposite direction. Reverse current. I could have left this out. It's just another tunneling. Imaging atoms. Where are our time-wise? Oh, it's 19 minutes, so it's close to starting a new video. Let's see if I can quickly do this one. Should I wait for it? It's gonna switch over to a new file now, the recording. Let's give it some time. Imaging atoms. Photograph. 19. Type of microscope. Imaging atoms. Field ion microscope. Tapered needle of tungsten, high voltage, and detected the ions emitted by the tip to form an image of the individual tungsten atoms itself. It's gonna switch to a new file now. Come on. 20, okay. There it's starting a new one. Okay, so imaging atoms. Field ion microscope. Field ion microscope. tungsten needle very high ions emitted. No, I don't understand. I mean, those, you don't have control over those ions. They will go everywhere, trying to get away from the needle. Are they the same? I think it creates the opposite ions, opposite charge. Platinum ions detected the ions emitted by the tip. I'm not sure what's going on here. Let's move on. 84. So you've got some high voltage setup with a needle and these ions created. Do the ions go to form image of the material underneath the needle or what? I don't know. Field ion microscope. Replaced scanning tunneling microscope. Please try and write decent. Replaced by the scanning tunneling microscope. How does it work? Nobel Prize. Tunneling between the tip of a needle and the surface of a material. So we've got the tip, the tip, material, tunneling current, moves horizontally across the surface. This misting fan is cooling me down. I need to put on something. Okay, that's better. It seems they move the needle across the surface. Height is varied. Keep the tunneling current constant. So it follows the contour of the material, I think. The mathematical surface formed from the height information is directly related to the presence and shape of the molecules and atoms beneath the tip's location. In fact, the atoms and zips can be moved by the STM to create atom-sized machines. Height of the tip. Is varied to keep current tunneling constant. Profile of a surface, I think, and also move. Organs move atoms. Let's move atom. Okay, imaging electron orbitals. Wave functions. Mathematical. Shape of these permitted regions. What now? They cannot. They thought they could not be observed. Clouds of probability. physical, they're not actually physical fields like electric fields. In 2013, a remarkable image of individual electron orbitals was achieved indirectly by Aneta Stodolna of the FOM Institute for Atomic and Molecular Physics in the Netherlands. Can be viewed. They don't say how, but they say can be viewed. Pencil is getting a bit thick, the lead. This is 2013. Huh? Is it? Yes. Netherlands. Aneta Stola. Quantum microscope, 86, 87. Quantum microscope. Quantum microscope. So they're going to tell us a little bit more how they did it. How they viewed the orbitals. Laser beam ionize atoms and trace the electrons from point of interaction with the ionizing photons back to the detector. What now? Okay, I have to get an idea of what they did. Thousands of the interactions and tracks the probability cloud for the hydrogen and could be built up. These cloud maps quantum your shooting equation as exactly as the noise in the data will allow. What? These cloud maps are far. Match the quantum calculations. How can you position it that accurately? Goodness gracious. Ionizing laser. Ionizing. They shoot electrons out in locations. Ionizing laser. Let's say we call it. They call it a beam. Ionizing laser. That means that the electron is shot out of the atom, and they don't say it like that, but that's what happens, I think. Yes, electrons came from detector. Okay, cloud maps. And got sort of idea. And now the monstrosity, quantum computing. Quantum computing. We need a book on that topic. What is going on there? Oh, the snowball's chancing now. Computers, calculations, software, switches. The states called bits can be fully on, off, algorithm. Can partition portions of the calculation. What? Algorithms can partition portions of the calculation and run them concurrently with other calculations, parallel computing, which greatly improves the speed of arriving at the final state. The algorithm can be thought of as taking a single pathway through all the possible intermediate states between the input and output to get the final answer. Classical computing. Parallel computing. So, parallel computing, the task is shared. While this one is doing that path is doing another part of the calculation. So you get at the answer much quicker. And concurrently, well, that's very difficult. I did some concurrent programming. It's it's a headache. Improves the speed of solution. Talking nonsense. Quantum computer connection between an input problem and an output solution. What is going on here? Input, output. Input is the problem, I think, and output is the solution. Parallel computing. Is that the various states? The end is in sight. 8788. I want to sharpen this thing a little bit. I'm going to pause it. Come on. Okay, we're back in business. Physicist Feynman, Yuri Manin gave a different approach to computing. Really? Feynman had a contribution there too. Normal computing bits and algorithms are called classical computers because getting from an initial state to a final state required only operations in classical physics involving switches that are either on or off, leading to a single efficient algorithm for reaching a solution for a calculation. Quantum computer, the algorithm takes all possible paths between the input and output state, and by the quantum process of superposition and entanglement, the most highly probable path becomes the most likely solution. So what should we say? Yeah. Algorithm. All possible paths. All possible paths, superposition. Now what is strange is that they bring entanglement into it. I don't understand. I think they said the input and the output is entangled. Yeah, that is because of the quantum nature. You're working with quantum units, and the process is running through this quantum system, so that's why it needs to be entangled. Okay, that makes sense. How on earth? Most highly probable path becomes the likely probability. High, most likely. Solution. To make this mode of computing possible, it requires not a two-state but a four-state qubit. Four-state. 1 and 0 are still, but superposed states between 1 and 0 also appear among the four possible states. Superposition. Quantum computers are prone to noise, so they have to be super cooled to cryogenic temperatures to prevent quantum states among the qubits from collapsing into random noise. Now, if there's interaction, then they can lose their states, they can collapse. Nevertheless, by sampling all possible solutions between the initial and final state and weighing their probability, this method can be extremely fast for some classes of mathematical problems, cryptography, and modeling the folding of proteins. What am I going to write? Most likely solution. Four-state qubit. No idea why they need four states. I thought it's more complicated than that, but somehow super cooled. Type of problem. First integrated quantum computing system of 20 qubits, a large quantum, have to confront a very difficult sublime issue called the problem of time. Currently no formal way to describe what it means for an observer to submit an input to such a computer and then later receive an output. No formal way to describe what it means. Shit. Oh, whoa, wait. This sounds like religion. Oh, I thought that was coming. Okay, what should I write here? Cryptography and molecular type of problem. This problem of time. Man. Okay. And just for fun, let's do 89. Where are we time-wise? Oh, I don't think I'm gonna make it. It's again going out. 89. Wants to create another file. Quantum tunneling. Radioactivity. Half-life. energy, atoms, quantum computing. Input, output, entangled. Effectively samples all logical possibilities at once to find a solution. All possible solutions. Possibilities. Possibilities to the solution. Advances in quantum computing hinge on answers to the very deep question quantum physics, such as the origin and interpretation of time. So origin and interpretation. Okay, we've tried to summarize it.